Okay, geometry. Today we are going to take our first crack at some actual geometric proofs. We're going to start with some segments, nice and easy, nothing too complicated. It's going to give us an idea of what we're going to be doing for the rest of the time we're doing proofs in this class. So before we get started, I want you to keep some things in mind because whether we're dealing with segments or angles or triangles or anything else, there is kind of a general strategy to these proofs that if you can keep that in mind, you will have some success. So, number one, I've mentioned a few times, always start with given information. We can't really start until we have that given information, whether it's just a diagram or anything else they want to give us, put that in first. Always end with what you're trying to prove. This lets your reader know that you're done, and also it just makes sense to end at the end. Okay, now that we're getting into geometry instead of just some algebra, we want to be making sure that we mark on our diagrams. Just trust me on this one. It makes it so much easier for your brain to pick up what's going on if your eyes see it. It just, I don't know, the human brain just works that way. Mark on your diagrams. It really does help. Okay, reasons column. So we got to be careful here. We should contain properties, definitions, theorems, or postulates. We don't want to just put a bunch of random nonsense into the reasons column. We don't want to put things that should probably be statements into the reasons column. We need to have a statement, and then that reason should be one of these four things. Your proof should flow logically from one step to the next. We shouldn't just be throwing things out in kind of random order. You should start with your given information and you should ask yourself, how does that given information help me? What statement can I make based on this given information? And then when you make that second statement, you should say, what statement can I make based on statement two? And sometimes it's going to take a couple statements to get to the next one. It depends on the proof, but you should be generally going in a top-down fashion. You should not be trying to bounce all over the place. One thing as we're getting into geometry here, keep in mind if you're working with objects or you're working with numbers. A couple reasons. One is the equality, the equal sign versus congruence, the congruent sign. So whenever we're working with numbers, we need to be dealing with the equal sign, and whenever we're working with objects, we need to be dealing with the congruent sign. There's going to be a lot of proofs where we need to switch back and forth between objects and numbers, and that is where your definitions usually come in handy. If you need to switch from a number to an object or from an object to a number, you should be asking yourself, what definition can help me here? Like the definition of segment congruence, anything like that, the definition of a linear pair. Just what can I use to really lay this out? And then finally, last step, don't panic. So just always be asking yourself, what do I know already? And what do I need to know, or what would I like to know? And then take that information that you already know and see if you can apply it to something that you need to know. And yes, that's pretty vague, but the more practice you get, the better you'll get at it. Just try to keep going in that logical flow, top down. All right, let's try a couple of these. So right here we've got a diagram. We've got this just line segment with A, B, C, and D all being collinear points on that segment. And we're given a little bit of information. We're given that B is the midpoint of AC. So I'm going to go ahead and put that in here. So I'm going to say that B is the midpoint of, and I'm actually going to use an equation here so I can use my line segment tool. AC. And in fact, if I wanted to make it look really nice, I could have made that B in the equation editor also. Okay, our reason here is that it is given information. We do have some more given information, so let's go ahead and put that down too. We know that AB and CD are congruent to each other. So let's go ahead and get that into our proof. So we know that segment AB is congruent to segment CD. Okay, now I've got both pieces of given information on here. So let's go to one of my other tips that I had for you. Let's actually mark on this diagram. So I'm just going to take my drawing tool. Maybe red will work here. So B is the midpoint of AC. So I know that AB and BC are going to be congruent. So I'm going to go ahead and use these marks right here to show that AB and BC are congruent. We were also given that AB is congruent to CD. So since AB is already marked with one red dash, I'm going to mark CD with one red dash. So it looks like we've got an idea of what's going on here. So we've got three segment pieces that are all the exact same length. They're all congruent to each other. If we can show that in our diagram with just a couple lines, or in our proof with just a couple lines, then we can show that C is the midpoint of BD by just kind of proving that BC and CD are congruent to each other, which we've shown with our marks. And this is why I say to mark up your diagrams, because now that I've done that, I'm looking at it and I know exactly what I need to do, and now I just have to put it into words. So let's see if we can do that. So let's take this first statement, B is the midpoint of AC, and let's see if we can get another statement on here. So I know that if B is the midpoint of AC, then segment AB whoops, that's not the symbol I wanted. Segment AB is going to be congruent to segment BC, just like I marked up here. And in fact, it would probably be easier if I moved this to the right side. Okay, so segment AB is congruent to segment BC, and the reason I know that is because there was a midpoint here. So my reason for this is going to be the definition of a midpoint. So I'm using one of those definitions as my reason here. Okay, now what we need to show is that BC is congruent to CD, which we've shown on our diagram, but we haven't shown with words yet. But let's look at this. We've got AB is congruent to CD, and we've got AB is also congruent to BC. So there is a property that we can use here. We are going to use the transitive property of congruence, because since both of these segments are congruent to AB, then they must be congruent to each other. So let's get the statement in first. So I want to say that segment BC is congruent to segment CD, and my reason for this is the transitive property of congruence. And something I could even do here is I could go in here and maybe in purple I can mark this one here and this one here, and maybe make myself a little note that says that these two lines together make it possible to say this line. So you don't have to do that, but this just shows the logical flow here. Okay, and then let's see, we're actually almost done. So if we've got BC congruent to CD, then we know that C is the midpoint. So let's put that as our statement. So we've got C is the midpoint of segment BD. And then how do we know that? We know that by the definition of a midpoint. And that was from this line here. So let's use a different color. Let's go maybe blue here and say that this line where BC is congruent to CD will directly lead me to this line right here. Because once I know that those two segments are congruent, then I can say that C is the midpoint by the definition of a midpoint. And that's it. I started with my given information. I ended with what I was trying to prove. Everything flowed downwards, and I'm done with the proof. So it takes a little bit of time. It takes a little bit of practice, but you can get it. All right, let's do one more of these. Okay, this time we've got two different segments, and we've got some given information. So let's go ahead and get that in first, and then let's mark on our diagrams here. So we know that segment AC is congruent to segment DF, and that is given information. And we also know that segment BC is congruent to segment DE. And that is also given information. So let's see how this helps us. So AC is congruent to DF. So I'm actually not going to mark this, but I am just going to keep it in mind that these two larger segments are congruent to each other. So just keep that in mind. AC is the same as DF, and they're lined up so it looks the same, so it makes sense, which is why I'm not going to mark it. But what I am going to mark is that BC is congruent to DE. So BC and DE are congruent to each other. I'm going to make some marks there, and then what I want to show, and maybe I'll put this one in like red. What I want to prove is that AB is congruent to EF. So this is my goal in red, and I just have to get there. Okay, let's see how we can get there. If there is, I guess let me just have, I'm going to put an open question here in the video when I actually upload this. What is your plan? Just give me a couple sentences, a couple ideas. It doesn't have to be like a fully fleshed out proof here, but looking at this diagram here, what is your plan to prove that AB is congruent to EF? Okay, so you've written down your plan. Hopefully you maybe mention the word segment addition postulate, because that is going to come in handy here. We're going to use that a couple times, and then we're going to do a little bit of algebra, and we're going to get where we need to go. Okay, so let's use that segment addition postulate here. Let's use it on the top line. We know that the segment addition postulate tells us that these two smaller segments, AB and BC, when we add them up, are equal to the length of AC. So we're going to put that as a statement. So I'm going to say AB plus BC, and notice I'm not putting a line over the top of these. If I'm just using two capital letters in a row, I'm saying the distance between those 2 points, so I don't need to put the line over the top of them, is equal to AC. And my reason for that is the segment addition postulate. And now I'm going to do the exact same thing for segment DF. I'm going to say that DE plus EF is equal to DF, also by the segment addition postulate. Okay, so we've got our numbers out here, And now we're going to use some of our given information to start combining these equations. So here's what I want to use. I want to use my first piece of given information. I know that segment AC is congruent to segment DF. So what I'm actually going to say here is I'm going to get really thorough, and I'm going to say that AC is equal to DF by the definition of congruence. So I had them as congruent segments, but now I'm also saying that their lengths are the same, because this is going to allow me to use the substitution property. So now I'm going to, and in fact, I'm going to go ahead and put two things in this line just to save myself some space, because I think I'm going to run out of lines otherwise. I'm going to say that AC is equal to DF, and I'm also going to use that second piece of given information and say that BC is equal to DE. And these are both the definition of congruence, so this is fine. If we're doing two things that are both basically the same with the same reason, you can put them in the same line. Okay, so let's start making some substitutions. So the first thing I think I want to do is go right here, and I'm going to make a substitution where I'm going to put in DF in for AC, which I'm allowed to do because I just said that AC is equal to DF. So I'm going to say that AB plus BC is equal to DF. And the reason I'm able to do that is the substitution property of equality. So just wherever I see AC, I can put in a DF because I've already stated that those two lengths are equal. Now I've got two different lines that are both equal to DF. So I'll put both of these in purple. So I've got this statement is equal to DF, and I've got this statement is equal to DF. And we're just going to take both of these and we're going to put them down here in this line. So we're still flowing downwards. So I can say that AB plus BC is equal to DE plus EF by the transitive property of equality. And we're going to run out of lines here, and that's no big deal. Sometimes this may not have been the shortest way to do this proof, but it's the way that seemed to make sense to me at the time. And if you run out of lines, just keep writing stuff below it. It's no big deal, because we definitely are going to run out of lines here, because I'm going to use this BC is equal to DE. So let's maybe even put another color in here. Let's go with a green. So BC is equal to DE, which means I can substitute it right here. So I can say that AB plus BC is equal to BC plus EF. And again, that was the substitution property of equality. Now I'm just going to keep going down here below. I want to get rid of these BC's here, because notice I want to prove that AB is congruent to EF, and now if we look, I've got AB on one side of the equation, I've got EF on the other side of the equation, so we are very close to proving them equal, and if we prove them equal, then they're also congruent. So in fact, now that's what I am going to say. I'm going to say that they're equal. AB is equal to EF, and the reason I'm allowed to say that is the subtraction property of equality. So I just subtracted BC from both sides of this equation, and now I've got AB is equal to EF, and then I've got one last thing. I'm not actually done here. I've shown that the segment lengths are equal, but I do want to show that these segments are congruent. So I need to put that last step in here and say that AB is congruent to EF. And just like up in line 5 here, I'm going to use the definition of congruence. So the definition of congruence, remember, states that if two segments have the same length, then they are congruent, or if two segments are congruent, they have the same length. It goes both ways. Okay, so there's our first look at a couple of geometric proofs. Make sure you bring me any questions. We'll get some practice on this in class, and I will see you tomorrow.